Hello, everybody. I just want to welcome you to Chapter 2, Part 1, Ventilation. This will be one of 4 parts in the Chapter 2 series on ventilation, Chapter 2 of Desjardins. So, the first thing we're going to talk about is ventilation. What is it? Well, it's just a mechanical process that moves gas between the outside or external environment and the alveoli or the lung. Why do we do this? Well, because we want to carry oxygen from the atmosphere to the alveoli so it can cross the capillary barrier, the alveolar capillary barrier into the capillary and be carried to our organs. And so carbon dioxide, the waste product from cellular activity, can be carried in the capillary system back from the cells to the alveoli and be delivered out to the atmosphere where plants and things like that can use it. Important to being an RT to understand that. So what do we as respiratory therapists have to understand? We have to understand how ventilation works, the elastic properties of the lungs, the dynamic characteristics of the lungs and how they affect ventilation. And dynamic means movement, so how the lungs move, stretch, and then characteristics also of the chest wall and how that affects ventilation. We're also going to talk about normal and abnormal ventilatory patterns. So let's start with the mechanisms of pulmonary ventilation. First, what is atmospheric or barometric pressure? How is it measured? Does anybody know? Do you remember maybe from your science course? What is a normal barometric or atmospheric pressure at sea level? If you said 760 torr or 760 millimeters of mercury, you're absolutely correct. So the abbreviation that you see, you can see the abbreviation PATM here. That is pressure, atmosphere. The other P sub B is barometric pressure. Those are interchangeable. So what is barometric pressure? It is the force exerted by air or gases that surrounds the body. All that weight of the atmosphere pressing down on our body at sea level. It's measured with a mercury barometer, pictured here. Atmosphere presses down on the mercury at the bottom of the tube and is read by how far up that pressure presses those mercuries. How many millimeters? At sea level, 760. In Denver, which is at a higher elevation, not as much of the atmosphere pressing down, and so your barometer would read less. Under the sea, I have not only the weight of the atmosphere at sea level, but I also have the weight of water. The lower I go down in depth, the higher the pressure will be. So, because weight of the atmosphere, P sub B, surrounds the Earth's surface and the human body, pressures in any respiratory area always are described as relative to atmospheric pressure. So if you're in Seattle, like I am, it's 760 torr. I'm at sea level. It does vary a little tiny bit every day, and we can look at a barometer if we work in a pulmonary function lab, and we can get the exact barometric pressure. 761, 758. It won't vary by much, but it does vary a little bit every day. So it's important that we get those absolutely correct readings. For a lot of things RTs do. So let's look at this, the difference between how the diaphragm works and where air is going to go. If I have a pressure of -4 millimeters of mercury in the trachea, then and I have and barometric pressure is 760, and I know the pressure in the trachea, because we're taking a breath in, is 4 millimeters of mercury less. How much pressure is that in the trachea? Well, I can simply take 4 from 760, and my pressure in the trachea is going to be 756. So 760 minus 4 is equal to 756. The pressure in the trachea is lower than atmospheric by 4 millimeters of mercury. So here's the opposite situation from what we had last time. We now have a positive pressure of 5 in the alveoli. And what does that really mean? Well, it means, one, if there's a pressure that's a positive pressure in the alveoli, then if we add that positive pressure to atmospheric, I have a total pressure of 765 in the alveoli. If my airway pressure in the alveoli is higher than what is in the atmosphere, where is the air going to go? It's going to go towards the area of least pressure, which means I'm exhaling. The air is going out. It's going towards my mouth and out into the atmosphere. So positive pressure of 5, 760, which is atmospheric, plus 5 is 765. My total pressure in my alveoli is 765. 765 and 760 means my air is going out, not in this time. It is going out. So if I have a zero pressure in the trachea or alveoli, and it is absolutely equal to atmospheric, it means that I have 760 outside, 760 in the alveoli or in the trachea. It means I'm at the end of expiration and I'm ready to start the process over. So this is an end expiratory pressure. So we're going to talk about pressure differences, or in other words, pressure gradients. Gas or liquid always moves from an area of high pressure to an area of low pressure. In pulmonary physiology, this pressure difference is called a pressure gradient. Gas always moves towards the area of least pressure, or down, we call it down, the pressure gradient, going from high pressure to low pressure. So a pressure gradient is just a difference in pressure. It can be as little as 2 or 3 units of pressure, or it can be 100 units of pressure, but it's just a difference between a higher pressure and a low pressure. The difference between a high pressure and a low pressure, area of high pressure and an area of low pressure, is called a pressure gradient. This is how we breathe, by creating pressure gradients between atmospheric pressure and alveolar pressure. Now let's look at expiration, when the opposite happens. So you're done taking a breath in, the pressures have equalized to about 5, and you're ready for the diaphragm to relax. The diaphragm relaxes, the air pressure the pressure becomes positive in the alveoli. Air moves out to the air. The air pressure is 760, is actually less than the pressure inside the alveolus, 765, because the action of the diaphragm relaxing created a positive pressure. So where does the air go? It goes out the mouth towards the area of lowest pressure. The bottom line is this: in order for either inspiration or expiration to happen, a pressure gradient for inspiration, in which the alveolar pressure is lower than the atmospheric or barometric pressure, and a pressure gradient for expiration, in which the intra-alveolar pressure is greater than atmospheric pressure, has to happen. This is how you breathe. So how does Boyle's law relate to all of this? Well, Boyle's law states that a volume of gas varies inversely to its pressure at a constant temperature. Well, that's a lot of words. What does that really mean? That gas volume will go up as pressure goes down, as long as we keep a constant temperature. So let's talk about what this is in the body. This is that explains how we breathe. Our body is a constant temperature. Check. As the volume of gas goes up in my lung, the pressure drops. What does that sound like? Inspiration. Of gas drops in my lung, its pressure goes up. What does that sound like? Expiration. So in this example, we're going to look at an airtight container, not the lungs which are open, but an airtight container with a volume of 200 milliliters and a pressure of 10 centimeters of water. If the volume is reduced by half, 100 milliliters, a new pressure in the container will double. So how does this work? Well, it works with the equation for Boyle's law. P2 is equal to P1 times V1 divided by V2. Well, what does all that mean? That means what do I want? I want to get my second pressure. I don't know that. What do I have? I have my first pressure, 10 centimeters. I have my first volume, 200 milliliters. I need to multiply those two and then divide by the new volume 2. So let's do that on a calculator. So in your calculators, I want you to put 10 times 200, and that's going to equal 2,000. 2,000 divided by 100 is 20. So my milliliters cancel out. I'm left with centimeters of water pressure. So this will be 20 centimeters of water pressure. Let's look at this in a picture, how this happened. So in my picture, you can see that my starting volume is 200 and my pressure gauge reads 10. So I'm going to take away half the volume. I decrease my volume. As you can see, it's being held at a constant temperature, but I decrease my volume down to 100 milliliters. I'm squeezing those molecules closer together. They're vibrating faster, and because the temperature is constant, they're creating a pressure. The pressure goes up. As the volume drops, the pressure goes up to 20. Doubling the pressure reduces the volume by half. The mechanisms of ventilation are often visually demonstrated by using a balloon in a bell-shaped jar, in Figure 2.4. The bell-shaped jar represents the rib cage or thoracic cavity. The rubber sheet across the bottom of the jar represents the diaphragm. The balloon represents the lung. The space between the outside of the balloon and the inside of the jar represents the pleural space. The trachea, which provides the only passageway between the inside of the balloon or lung and the atmosphere, is pictured by the cork at the top of the jar and the straw to the balloon. So let's talk about first what happens in picture A. To simulate inspiration, the diaphragm is pulled downward, causing the size of the thoracic cavity to increase, increased volume, which in turn causes the pleural pressure to decrease. Remember that according to Boyles' law, as volume increases, pressure drops. Because the balloon is composed of a very thin, stretchy, rubbery material, very like the elastic properties of the lung, the pleural pressure is transmitted to the inside of the balloon. This mechanism causes a pressure gradient or pressure difference between the inside of the balloon and the atmosphere. Because atmospheric pressure is higher than the pressure inside the balloon, that is, a pressure gradient, gas from the atmosphere moves down the tube into the balloon. The gas continues until the pressure inside the balloon equals the pressure in the atmosphere. That's called the equilibrium point or zero pressure point. Once the equilibrium point is reached, gas flow stops. This period of no gas flow represents end inspiration, pictured in B. To simulate expiration in picture C, the elastic diaphragm is allowed to recoil. You can see the hand letting go of the diaphragm. It causes the size of the thoracic cavity to decrease, decreased volume, which causes the intrapleural pressure to increase. Remember, according to Boyles' law, as volume decreases, pressure increases or rises. Volume drops, pressure rises. Again, because the balloon is composed of a very thin rubbery material, the increase in pleural pressure is transmitted to the inside of the balloon. And this mechanism causes a pressure gradient between the inside of the balloon and the atmosphere. Because the pressure is now higher inside the balloon than the atmosphere, that is, a pressure gradient exists, or pressure difference between the atmosphere and the balloon, gas from inside the balloon flows out through the tube and into the atmosphere. Gas will continue to flow until the pressure inside the balloon equals the pressure in the atmosphere, pictured in Part D. Once the equilibrium point is reached, the gas flow stops. This period of no gas flow represents end expiration. Again, this is pictured in Figure 2.4, Part D. The entire simulated breathing sequence, that is, inspiration, end inspiration, expiration, and end expiration, represents one respiratory cycle. This mechanism causes a pressure gradient to develop between the intraalveolar pressure and the atmospheric pressure. because the atmospheric pressure is higher than the intraalveolar pressure, that is, a pressure gradient exists, or pressure difference, gas from the atmosphere moves through the tracheobronchial tree to the alveoli. This gas flow will continue until the intraalveolar pressure and the atmospheric pressure are in equilibrium. Once equilibrium is reached, gas flow stops. This period of no gas flow is called end inspiration or pre-expiration. It is the end inspiration phase of the respiratory cycle. During expiration, the diaphragm relaxes and moves upward, causing the size of the thoracic cavity to decreased volume. This action causes the pleural pressure to increase. Because the lung is composed of such a thin, elastic material, the increase in pleural pressure is transmitted to the inside of the alveoli, which in turn causes the intraalveolar pressure to rise. This mechanism causes a pressure gradient or pressure difference between the intraalveolar pressure and the atmospheric pressure. That is, a pressure gradient exists or pressure difference. Since that's true, gas from the alveoli moves through the tracheobronchial tree out to the atmosphere. The gas will continue to flow until the intraalveolar pressure and the atmospheric pressure are once again in equilibrium. Once the equilibrium point is reached, gas flow stops. This period of no gas flow is called end expiration, or the end expiratory phase of the respiratory cycle. So I have a question for you. At what point in the ventilatory cycle would the intraalveolar pressure be higher than the atmospheric pressure? It's during active expiration, because by the time you get to end expiration, the intraalveolar pressure is equal to barometric. So that's the end of part 1. Thank you for your attention, and I hope you have a great day.